Hey everyone, and welcome to The Explainer. I am absolutely thrilled to have you here today. Look, if you're the kind of focused learner who loves taking how the world operates and breaking it down into really clear, actionable concepts, you are in exactly the right place. Today, we're exploring the foundational physics that basically govern our entire lives: work, energy, and power. And I promise you, by the time we finish up, you're going to look at your daily routine through a completely different, highly scientific lens.
Okay, let's dive into this. Picture someone who is just studying for hours, reading books, drawing diagrams, organizing all their thoughts. In everyday language, we'd say they're really working hard, right? But in the realm of physics, they might actually be doing zero work. Now imagine you just walk up to a tiny pebble on the sidewalk and give it a little push with your shoe, moving it maybe a few inches. Scientifically speaking, you have just done work. Kind of wild, right? Well, that's because the strict scientific definition of work requires actual physical displacement, not just mental or physical exhaustion.
So here's our mental roadmap for today's explainer. We're going to start with the scientific definition of work, move into energy as our universal currency, compare kinetic and potential states, look at the grand conservation of energy, and finally, wrap up with power. Think of these as building blocks that just stack perfectly together. All right, let's get into our first building block. Section 1. The scientific definition of work. Let's look at the exact conditions required for work to actually happen. What's really interesting here is that two things absolutely must occur. A force has to act on an object, and that object must be displaced. It has to move. Let's say you decide to push against a massive giant boulder. You push with literally all your might. You're sweating, you're completely exhausted. But if that rock doesn't move a single millimeter, despite all of your intense physical effort, you've done zero scientific work on that rock. The displacement was zero, so the work is zero. And here is how we map that out mathematically. Work equals force multiplied by displacement, or W equals F times S. You know, this formula isn't just some boring math problem, it's practically a universal recipe for how our physical world operates. Oh, and the end result? We measure that in a unit called joules. To put that into perspective for you, exactly 1 joule of work is done when 1 newton of force moves an object exactly 1 meter. It's a super precise, measurable transaction in the physical universe. But this actually brings up a really fascinating question. What is the currency required to actually perform this transaction? Which leads us perfectly into Section 2, energy, the capability to work. Energy is quite simply an object's capability to do work. And because it's the currency we use for work, it's also measured in joules. Think of it kind of like a bank account. The object that does the work spends its joules. It loses energy. Meanwhile, the object having the work done to it actually gains energy. Like if you lift a heavy box off the floor, you're spending your own biological energy. But that box, it's gaining energy simply by being lifted. Moving right along to Section 3, kinetic versus potential energy. So, what forms does this energy actually take in our everyday lives? Think about this for a second. Where does a stretched bow get its energy to shoot an arrow at such crazy high speeds? When it's just sitting there drawn back, it isn't moving at all. Yet the literal second you let go, it unleashes a tremendous amount of force. How exactly does that energy get stored up? Well, the answer is potential energy. This is the energy an object has simply by virtue of its position or some change in its configuration. When you pull back that bowstring, you're changing its shape, and the work you did gets stored right there in the string as potential energy. Same thing goes for lifting stuff. When you lift a book up above a table, going against gravity, it gains gravitational potential energy based on its new height. On the flip side, we have kinetic energy, and this is all about motion. A falling coconut, a speeding toy car, the wind blowing. These all have the capability to do work entirely because they are moving. An object moving really fast can do way more work than the exact same object moving slowly. But simply, motion equals kinetic energy. And this brilliantly illustrates the difference between the two. Think about the formulas for a second. Kinetic energy relies heavily on velocity. That v squared means speed is the absolute dominant factor here. Meanwhile, gravitational potential energy relies entirely on height, the h variable. Mass and gravity, those are just constants. But the higher you lift something, the more potential energy you stash away. All right, let's look at Section 4, the conservation of energy. Guys, this is the grand rule of the universe when it comes to how these energies interact. It dictates that in a closed system, energy can only be converted from one form to another. It can literally never be created out of nothing, and it can never be destroyed. The total mechanical energy before and after any transformation, it remains perfectly mathematically constant, always. Watch how this actually plays out in the real world. Imagine dropping a heavy 20-kilogram weight from a roof. In step 1, right before you let go, its potential energy is totally maxed out. But because it isn't moving yet, its kinetic energy is 0. In step 2, halfway down, it's lost half its height but gained a ton of speed, so potential energy has just seamlessly traded off into kinetic energy. By step 3, right before it hits the ground, height is 0, so potential energy is 0, but its speed is at maximum, meaning kinetic energy is at its absolute peak. The total amount of energy never changed. It just changed costumes on the way down. And that brings us to our final building block, Section 5, Power, the speed of work. So we know how work happens and the energy required to do it. But what about the rate at which we actually spend this conserved energy? That is where power comes in. Power is just the rate of doing work, or how fast energy gets transferred. Imagine two people who weigh the exact same, both climbing an 8-meter rope. They are doing the exact same amount of work because the force and the displacement are completely identical. But if climber A reaches the top in 15 seconds and climber B takes 20 seconds, climber A expended more power. Same work, she just did it faster. Mathematically, we express this as power equals work divided by time. By taking the total work done, or, the total energy consumed, and dividing it by the time it took to do it, we find our power. And the unit we use for power? Watts. So the crucial point to remember here is that exactly 1 watt is the power of an agent doing work at the rate of 1 joule per second. 1 joule, 1 second, 1 watt. But honestly, in our everyday lives, 1 single watt is pretty tiny. So we usually express larger rates of energy transfer using a multiple of 1,000. 1,000 watts equals 1 kilowatt. And that's the practical scale we use for things like electric vehicles, big industrial machines, and everyday household appliances. Which actually connects directly back to your own home. Have you ever looked at your electricity meter outside? If you take a reading at 6:30 in the morning and another at 6:30 at night, you're going to see a change in the units. Well, those units on your monthly power bill are simply commercial measurements of energy consumption over time. Specifically, they're kilowatt hours. You're quite literally paying for the physics of power and work happening inside your appliances. Okay, let's quickly summarize the amazing building blocks we've covered today. Force plus displacement gives us work. Doing that work requires a currency, and that's energy. Energy stored by position is potential, while energy from motion is kinetic. Remember, that energy is constantly transforming, but it absolutely never vanishes. And finally, the speed at which you transfer that energy is your power. It's just this beautifully structured, totally closed cycle of physical laws. Before we wrap up, I want to leave you with one final, slightly mind-bending thought. We established earlier that you do 0 work on a giant rock if you push it and it doesn't move. But we also know you feel completely exhausted afterward. So if energy is never actually destroyed, where exactly did all your biological energy go if it didn't go into moving the rock? Think about the heat radiating in your muscles or your massively increased heart rate. The universe always balances the books, one way or another. Keep observing the world around you, keep asking these kinds of questions, and I'll catch you in the next explainer.